Professor Sally Cripps, who is a statistician. She's our director of the DARE Data Analytics for Resources and Environments, which is an ARC Industrial Transformation Training Centre. But today, Sally will be talking about some work that she has also been doing on COVID modelling, which has been published in the Forecasters Journal. So I will just get that presentation up and then I'll hand over to Sally.
Okay, well, thanks very much. Yes, it's my great pleasure to talk about some of the work that I've been doing. So just as a bit of background, the International Journal of Forecasting actually has a debate going, or actually organised the debate between have the models failed? And this was largely around US data, so I'm going to be focusing on the US in this context. They chose Johnny Ioannidis to lead the affirmative team, saying yes, they failed. And then Nassim Taleb is in charge of the opposition team. The idea here is to get the debate out in the open, to air these things so that we can have a discussion around what actually the models benefited us, if they benefited us, and in what ways they may not have benefited us, if that's the case. And I can, you see down on the graph on the bottom right-hand corner of the screen, these are graphs that you'll probably be so familiar with by now. You know, that's the number of daily deaths in the USA. And I've stopped it as of the beginning of June, and the rest are forecasts from various models. And you can see that those daily forecasts range from, 5,000 to, I can't actually, because I haven't got my glasses on inside. Can I get rid of this screen back a bit? To some very large number. And I suppose what I want to talk to about today is how useful those things is, and really how difficult it is to make decisions in such a huge amount of uncertainty. And in doing so, I want to acknowledge that it is so much easier to criticise models than to come up with them. And I think one of the great things that I learned about this work was just how brave and public-minded the groups who are doing these models are actually, by putting their forecasts out so that everybody can evaluate them, by giving predictive distributions. Without that, I think we would learn far less. So you can probably guess what my takeaway from all this is up front. I want to start by saying, okay, so there is to date 120,000 deaths in the US. So Johnny Ioannidis, he is a very eminent epidemiologist, probably one of the most cited in the world, said in April that I would say that COVID-19 will result in fewer than 40,000 deaths in this season in the US. And he said, my quote appeared on April the 9th, and I sadly behaved like an expert. Journalists and the public want certainty even when there is no certainty. So that's one estimate, which was 40,000. And as he says, he made it because he was incorrect, but people seem to want certainty. And so I suppose this is what this conference is about, is trying to get people to accept that there is uncertainty, and so stop clinging at numbers as if there is. An equally eminent public health specialist said that we would have 100 million cases of COVID, doubling every day. So that was on March the 27th. So on one hand, you've got a forecast of 40,000. On the other hand, you've got a forecast of 100 million. Both of them, I think, actually just go to just how difficult it is to make predictions for a novel virus that we've never seen before in the complex world that we live in. And this is a quote from the paper. We've said that we come to basically the same conclusion, except I think there are certain nuances that are different with Gideon's talk. But a wrong doomsday prediction may incentivize people towards better personal hygiene. But the problems start when public leaders take wrong predictions too seriously, considering them crystal balls without understanding their uncertainty and the assumptions that they made. And so to pick up on Gideon's talk, how useful were they? And in what sense did they inform decisions? I think on occasion has had catastrophic implications for the US, and I'll talk about one of those ways in which the models were used to the detriment of the health of US citizens. So just to answer the question, did they fail? So I'm going to answer this by actually defining what we think about failure. So the first way, probably the most naive way to think about failure, is predictive accuracy. So so what I've got here is the percentage of 7 day ahead. So these were forecasts that were made, say, on the Monday for the following Monday, that fell within 10% of what actually happened. So these are not hugely long-term forecasts. So they're just within a week. And we had a look at 4 models, and I'll briefly explain what those models were. Or what they called. The top left-hand one is IHME. It's the Institute for Health Metrics Evaluation. That's out of the University of Washington, funded by Bill Gates. The other one, the LANL, is the Los Alamos National Laboratories. The bottom left is the University of Texas, and the bottom right is YYG, which is from MIT. They both have different approach. They all have different approaches, and we can talk about some of those approaches later. But essentially, what you want when you're looking here, if you look at that scale, you've got blue means that they almost got no predictions within the 10%, within 10% of ground truth 1 week ahead. The top is red, and that means that they got over 40%. So if you look at this, I think you'd have to say for predictive accuracy for a week ahead, the models were not great. I think it would be hard to say that they accurately forecast, and I'll talk about why they were also so bad. This is just 1 day ahead. So this is just using the model. So again, we're not talking about so this is, unlike what Gideon talked about, this is not sensitivity to initial conditions. What about if I got R0 wrong? These are people that are making the model prediction. They've got all the data available today, and I want to tell you what that model said tomorrow, how much it predicted it tomorrow. Again, there's very little difference between going from 7 days to 1 day ahead in terms of forecast accuracy. They're still doing very, very poorly indeed. So I want to now talk about, well, okay, so everybody is quite comfortable with the fact that a prediction, which is sometimes called a point estimate in statistics, is just that. It's just a point estimate. And of course, they're not, it may be asking too much of them to be within 10% of that, of the ground truth. But then we ask the question, because all these models, we chose them because they provided not just point predictions, but also prediction intervals. Again, I want to stress just how difficult that is to do. And so the fact that these models put those values up there is to be commended. But if we have a look at it, what these are is the percentage of 1 day ahead. So this is, I'm going to predict tomorrow. The percentage of 1 day ahead forecast that fell within a 95% prediction interval. So we've got, we would expect for 95% of forecasts to fall within a 95% prediction interval. In general, the amount of forecasts that fell within a 95% prediction interval was consistently, except for the University of Texas, was consistently below 50%. So they're not just getting point estimates wrong, they are also getting the coverage wrong. So we are seeing that if you define failure in terms of uncertainty quantification, they got it wrong. If you define failure in terms of being accurate in the prediction, they got it wrong. And so does that really matter? So are they useful then in some sense, given that they performed on those 2 measures very badly? So when we came to think about this, it's a very difficult graph to see. We had a look at New York. So this was a case study in model failure. What I want to do here is actually highlight a couple of things. So the governor, Andrew Cuomo, said, on March 24th, I don't have a crystal ball. Everybody's entitled to their own opinion, but I don't operate on opinion. I operate on facts and on data and on numbers and on projections. And by May the 25th, he said, now people can speculate, people can guess. I think it's next week, I think 2 weeks, I'm out of that business because we all failed, right? All the early national experts, here's my prediction model, they were all wrong. So we've got somebody going from being very pro the models on March 21st to March, the end of May, being, you know, obviously disillusioned with the ability of models to actually deliver what he thought needed to be delivered. And in a large respect, he was right. So what I've got up there, which is probably, I might switch to the next slide because that's actually just too many plots on one side, you probably can't see it, but these are, just to go through it, each column represents how many days ahead the forecast was. So we go from 1 up to 7, and each row represents the different models. You can, and we'll come to the IHME model is the top one. The next one is, is LANL, is the Las Almas one, then University of Texas, and then the YYG. They're basically showing that we didn't do such a great job in terms of predicting deaths. But, you know, does that matter? And for that, I'd like to say, well, now let's go to ICU bed usage, because the models are used to inform resource allocation. So they're not just used as a guide, but, you know, how much ICU bed usage should I have? And these were models that were predicted by IHME. Just to run you through what these things are, each box represents a date. So the first one is the 25th of March this year. The second one is the 26th, and so on up to the 31st of March. On the axis, on the y-axis represents the predicted bed usage by the model, which is the black line, together with its uncertainty prediction or 95% prediction interval, which is the grey shaded area. The red line is the truth. And what you see there, they start out very unsure. You see that the red line, initially the model is over predicting the number of hospital beds or ICU beds that are needed. And as you move along the x-axis, you go from April through to July. That's when they ran their model. You can see that later in the piece, it is grossly under predicting. I suppose what I want to take away here is that this was on the 25th of March. So if we move to the rightmost graph, that's the 31st of March. You can see one thing has changed in the forecast, which is they've got more certainly wrong about what the actual predicted bed usage was. So you go from a very broad grey band on the 25th to a pretty much the same sort of prediction, but a bit higher on the 31st and a much narrower interval. And you can say, well, does this really matter? And I would say, yes, it does, because on March the 25th, the decision was made to discharge 4,500 COVID-19 patients to nursing homes in anticipation of beds being needed. So this was a case of resource allocation decisions based not only on the models, but they were talked about in the press at the time. They were on the CNN news. The White House talked about this particular model. It had a big impact on the way people thought about what they would actually need. So as you know, that nursing homes are full of highly vulnerable people. And so this decision, based on model predictions, which were wrong, resulted in several deaths. So over in New York, you know, over close to 6,000 deaths occurred in nursing homes. So that's, I suppose, an example of where a model has most definitely not been useful. And Gideon obviously, you know, he focused on the ones that have been useful. He didn't say that they were all useful. So what went wrong with all these models? Well, a lot of it is poor data. You know, when you have a look at modeling New York data, there were 5 different ground truths, all of which were spectacularly different. So it's not a surprise that if you use very poor quality data with very different, you know, different data, you'll get different outputs and incorrect predictions. There's a lot of wrong assumptions, mainly around homogeneous versus heterogeneous population. There was a lack of incorporating sometimes the epidemiological features of the population, selective reporting. Most particularly, it was the poor uncertainty quantification. And so I just want to move your eyes now to the bottom right-hand graph. This is a graph of the predicted daily deaths in New Jersey. The red line is the truth of what happened. The blue line is the blue shaded area, and down the bottom there was the initial prediction of what the deaths were going to be and the uncertainty around those deaths. So in other words, they were initially, this particular model, this was IHME, was predicting deaths highly certain. And then they realized they were predicting deaths that were highly uncertain. And the prediction interval there ranges somewhere from between 200 deaths a day to 2,500 deaths a day. And again, I would say this is not a useful model. I think if you're getting those levels of uncertainty, then it's not particularly useful for public policy making at all. You're better off ignoring uncertainty intervals. You don't need a fancy statistical model to tell you that the daily deaths are going to be somewhere between about 50 and 2,500. I suppose what I think is the biggest problem with most of the models that were used was this lack of multi-criteria objective functions. And I'll talk a bit about that in the next slide. That is, what is it that we want to actually achieve from these models? There's been a lot of talk now. There's been a lot of talk about reopening the US. We had this top quote in a paper where they predicted an additional 233,000 deaths. The number of total deaths as of yesterday is 120,000 approximately. So they're clearly overestimating it. But just before we get too carried away with the fact that we should unlock and that lockdown doesn't work, I'd like you to look at these bottom graphs. These are actually from the Imperial College, but they are based on their models, but also actual data. So you can have a look at the one on the left-hand side. That is looking at the number of deaths is the pink chart, the pink bars, and we have the dark blue line and the not so dark blue line representing 95% credible and posterior intervals respectively of what the actual deaths were. So that is looking fairly good. What is not looking so good is the number of incidents, but let's move on to the right-hand panel. This is, by the way, I should have mentioned, this is Wisconsin data. Now, the reason I've chosen this particular state to look at is because this is often touted in the US as an example of where lockdown had no impact because they took they removed a lockdown on May the 11th. What you can actually see here is that if you look at the deaths, that there seems to be an upward swing in the number of deaths. The right-hand panel is the RT, that's the reproduction rate, so how many people would be infected if if one person is infected. And you can see now that has now crept up above the critical value of 1, probably following the release of the lockdown issues. So this gets me to the a lot of million-dollar question is, should we, what does this mean about lockdown? And that's a tricky problem. And fortunately, it's not mine to solve, other than to say that there is many things that we have to think about. So there is no doubt that lockdown will reduce the number of COVID-19 deaths because it will reduce the spread. So it will reduce the number of deaths. The question is, what else does it do? And sometimes what else it does is not quite so visible or quite so easy to measure as COVID deaths. And these are the things that I think are facing policymakers at the moment, and they're very difficult. People often ask me, well, when we looked at COVID, how terrible they were in the US, what do I think about Australia? And it's impossible to answer that question because nobody in Australia will actually make their forecasts public to the degree that they can be evaluated in the same way that they were. So, you know, what did we do right in Australia? I think that there is, I think that we are lucky to be an island. I think 60% of, well, you can look it up, 60% of our cases are from overseas, and we've had a very good quarantine system. I think the virus came late to us, and we were therefore locked down quickly in relation to the number of confirmed cases. I don't think, you know, I think when you're faced with a global pandemic of possible 50 million deaths, then early and immediate lockdown is totally justifiable. Then decisions, and I come to my last point, which is that decisions around the management of COVID-19 in Australia have largely not been politicised, and I hope that remains the case. And that's very different from the US. I think one of the things that we've done well in Australia is that we have put politics aside and got on with thinking about how we can manage this situation. So, key takeaways. In terms of accurately predicting, accurately quantifying predictive distributions, most certainly the models have failed. In terms of informing debate, and I think this goes to Gideon's point, I think that they've been a success. However, and this refers to Andrew Gelman's point earlier, modelers need to acknowledge when we've had predictive failure. Because if we don't, then if we spend our time justifying bad models, then we miss opportunities to see how to improve. Another key takeaway is we must have better and more timely data. If we are to use models for policy making, their performances must be evaluated against real-time data repeatedly. When we have a look at which drugs are going to be working for COVID-19, we don't just take somebody's prediction, we actually have some evidence that they have had some performance. So maybe some system where if bad performing models, you know, having a look at whether or not how they've gone for the last week, therefore that if they've performed badly, then we should be dropping them from the policy making pot of models, if you like. So we must evaluate them against real-time data. Most importantly, we need to think about models which have multi-criteria objective functions. As I've said in the last slide, lockdown will decrease COVID deaths, but the costs of doing this are less public and less easy to quantify. And I would add that actually our wanting to focus on a single outcome, which is COVID deaths, in itself is a product of our desire for certainty. If we can see that number coming down, then we feel that we've got something under control, even if there are some things that are running out of control that we're not noticing. And I don't mean to say that this is a criticism. I think this is just being a human being. You know, I like to go to the gym to run because I can see the miles and the calories tick over rather than running around outside. So, you know, I think it is a product of being a human. We want this desire for certainty, but it does lead us to being narrow-minded in our objective functions about what we want to maximize. The other key takeaway, the modelers who made their predictions and code publicly available should be commended. But in general, I think the modelling community should be a little more humble than we have been. We should acknowledge what is not known and try to identify and quantify uncertainty. We should under-promise and over-deliver, not the other way around. We must admit when we get it wrong, because that's how we learn. And if we fail to do this, and this is my big fear, we will undermine the public trust in science. I'd like to end on my favourite quote from my favourite scientist, Richard Feynman, who said, "We will not become enthusiastic for the fact, the knowledge, the absolute truth of the day, but remain always uncertain, because in order to make progress, we must leave the door to the unknown ajar." Thank you.